Hello and welcome to CSE259 recitation. Today we'll be discussing about task 3 and task 2 and task 3 of the project 2. Before we jump into the two tasks, a quick overview of task 1. Hopefully, after the previous recitation, you have been able to implement some aspects of task 1. So the project contains 3 tasks. It's to implement a game of chess. Task 1 is to create a visualization of the board. Task 2 is to implement the player A, that is the white player's moves, and task 3 is to automate the game between the two players. There is a part of the code in chess.pl where you need to implement your code. It is given to you as implement your code here. So this is provided for you for task 1, 2, and 3. So this is the location for task 1, where you do the visualization of the board. So after the first step of executing the code, this is what you should see as an output. This is the initial state of the board. So in the last recitation, we went about building a separate file called gameboard.pl, which would output the initial board. Now this code can be copied and integrated into your location of code over here. And once you paste it in, just watch that you don't repeat certain lines of the code which are already available to you under chess.pl. So the functions such as this main have been provided. Hopefully you remember the function myMember, which checks if a particular pawn or a coin is available in the current state of the board. And the state of the board is defined as a list containing the cell number or the cell value, for example, A8, containing a black rook. So this is a small overview of the code where you say draw content cell and it outputs the coins that are available on the cell and also draws the entire board using dashes and pluses and pipes and spaces. So copy your code into your chess.pl before you move into the next task, that is task 2 or task 3. So let's now jump into task 2 and task 3. So here is an overview of the flow of the code for task 2, task 3. This is not a flow diagram, but it is just to give an initial view of what are the various aspects of the code. So you call a function main, and main first initializes the board and sets the initial state. The initial state is, as you would have seen it in this board over here, with the pawns set in the base state of a chessboard. It then calls play. Play calls a function called execute move. Execute move looks at the board and calls a function called respond to. Respond to depending on the player's move, whether it is player A as the white player or the player B as the black player of the black coins. It decides what to do. So the first thing that respond to calls is something called a select move. Select move, we will see further into what select move does in the following slides. Select move finds the best move that has to be done and commits that as the move and produces that or returns that to respond to. Respond to uses this to call finish move. Once the best move is identified, it calls finish moves, which updates the new state of the board. And this again calls execute move. This loop continues until the game is over with a checkmate. So now let's dive into each of these functions and how you should understand them and go about implementing your code. So respond to, as we saw, calls select move. Select move is based on the player. So is it player A or player B? You can give it the current board state, then you can give it a move from 2. And it also takes in something called a rating, which decides is based on the algorithm that we will be seeing in the future slides. One important thing that you need to know is you can also provide a state or a move that can be performed by the system in case the board is in a particular state. For example, here, if you have this particular state, that is, the pawn at e2 is moved to e4, then book B decides that player B has to perform this move, that is e7 goes to e5. You can predefine certain moves of this type. This is useful if you believe that a particular state of the board with a single move can help you get a checkmate, which would complete the game for you much faster. Or if you want to start with an initial move. Similar to book B, you will have to define a book A in case you need moves which are predefined for player A. So task 2 requires you to define the moves for player A. The moves for player B have been defined. The code is available. So you can have a look at the code provided by for player B and then work out the moves for player A. So this is the code available to you for player B. Using this, you can learn and write the code for player A. The main algorithm for automating things in this is based on the min-max tree algorithm. In fact, we use the min-max with alpha-beta pruning. So let's try to understand what is min-max and what is min-max with alpha-beta pruning. So look at the simple problem of tic-tac-toe. So given the initial state of a blank board, the idea is to decide what would be the next move. Now, there are two players who are playing this. Player 1, which is you, is trying to maximize your score when you're playing the game. And the opponent is trying to maximize their score, or in other words, minimize your score. So if you look at this, in the initial state, there are 9 possible locations where you can put an X. The idea is to decide which of these would give you a maximum chance of winning. And the player 2 tries to put an O based on your move. And his idea is to see that he minimizes your chance of winning and maximizes his chance of winning. So you will see an alternation of a max and a min, max and a min, until you reach a final state of winning. How is the score calculated? The score is calculated as a backpropagation of the utility values which are given to the terminal state. A simple utility that can be thought of in case of a tic-tac-toe is where the opponent wins is given a value -1, a draw 0, and your win as a +1. Well, these utility scores are to be defined by you. One interesting fact is that there are 9 initial moves possible for a tic-tac-toe. How many are possible in case of a chess game? Initial. How many will be there when you move to step 2 or the second move? How many possibilities exist? How does it grow? That's something you need to think about when you are going to implement your min-max algorithm. So here is how the min-max algorithm works. So the first step, as we saw, is to maximize. The second step is to minimize, maximize, and you reach your utility scores. So what does the maximizing do? It looks at the utility scores and chooses the maximum of the possible branch. So that's a 0.9. Now let's assume that this happens across for each of them and you get a 0.9, 0.8, and a 0.9. The minimize tries to minimize these 3 values. So it picks up the minimum of these three, which is a 0.8. And now your duty as a maximizer is to see that you take the maximum of the values of the next state. And this is how the Minimax algorithm propagates the utility values back to the top. Now there is a simple issue that you can see right here. Expanding all possibilities as we thought of in the previous case of tic-tac-toe would give lots and lots of moves. In order to decrease this, they implement min-max algorithm with alpha-beta pruning. So what is alpha-beta pruning? At any point of time along the maximizer's path, alpha is the best option or the highest value that can be taken. Alpha is first initialized to a minus infinity. Beta is the minimizer's value, and it is the lowest value that it can take. And beta is initialized to plus infinity. We always take it that alpha should be greater than or equal to beta. The algorithm tries to maintain this throughout. And in case this does not hold, you don't go down that path. The alpha and beta values for each node must be kept track at the node level. Well, you see that this adds an small amount of extra data requirement. But since we would not be pruning the rest of the trees, we would not be going about seeing the rest of the values, we would save a lot of space in terms of identifying what would be the children of all the trees. So in this case of the previous step, you see that there are 0.9 is the value that is taken over here. The initial value of alpha is minus infinity and beta is plus infinity. This is brought down all the way. And then looking at this 0.9, you see that 0.7 and 0.3 are not considered. So what happens over here is we don't need to expand these values. And hence, alpha takes the value as maximum of minus infinity and 0.9, and beta takes the value, remains plus infinity. In the next step, you try to see which of these values is picked up. Since it's the 0.8, you don't end up touching the 0.9s, and this results in this value as alpha being 0.9 and beta being minimum of infinity and 0.8. And here you see that alpha is greater than beta. So in this way, what we would choose is to expand the tree 0.8 and not expand either of the 0.9s. This is the basic idea or the intuition behind alpha beta pruning. The algorithm for alpha beta pruning has been provided for you in your code. Now the idea for you is to understand alpha beta pruning, the code of player B, and implement the code for player A. So let's just have a quick look at the code of player B. Player B, when you call select move, it chooses the third state in select move, that is to find an automated response. This is based on a function called strength B, which defines or decides the strength of a particular move. And the idea is, as we saw, to choose the move with the maximum strength. And this move is returned back to select move as the best move to be done. The idea of how best you would search below is based on this definition called ply depth 3. Now this depth is for player B, and you can define your own for player A. The values for having a particular move, like that of a king moving to a positive or reaching a state where the king has won, gives a 10,000 points. And similarly, capturing various others have points below. So these, based on these values, the strength is calculated back. Now the code for book B is provided. Similarly, you need to implement something for book A in case you want to make a move. And looking at these codes where you have the alpha and beta pruning for player B, you need to work out what would it be for player A. You may go through some issues with the amount of memory space available in player in while running the code. So one thing you may want to do is increase the amount of stack variables that you have. This can be done in for Windows by going to set memory size and changing the appropriate local stack and other registry values. This is in case of Windows. In case of Linux or Mac, you can use this command at your command line. Well, in both the cases, you will have to restart your gprolog to have or to for these variables to have an impact. Now, before we go into task 3, let's look at how task 2 would run. So based on this, I have done a small implementation of player A code, and let's try to execute player A code. So let me go to File, Console, let me just go and execute my code. So that's it. And let me type main. So it's drawn the initial board for us. Now to run the next command, I need to provide the input. So if you remember, I was saying E2 to E4 was the command that we chose. E2 to E4, and remember, I need to provide a dot whenever we provide an input in Prolog. So it executes the next state. It displayed the state of the board and also provided the current state as a diagrammatic view. Now it's for me to choose what I want to do. So I can move Q from D1 to H5. So you can say D1 H5 dot. Is that right? D1 to H5. Enter. So that's what is the move that we chose. And black has moved D7 to D6. So this is how it would execute and every time wait for you to perform the move. So this is the end of task 2. Now let's have a look at task 3. While executing these commands, what's happening here is it's calling a function called get command, and get command asks you what's your move, and this is for player A. Now the idea is to remove this get command and automate the player move for player A. Remember, this is already happening for player B. Instead of a command, it is calling player B. So you need to make those changes so that instead of it calling get command, it will execute command for player A. This will complete task 3 for you. It's quite simple to do, and it's more about understanding the code that is over there under task 3 than executing or writing your own code. So here is the code for the initial running of the program. Understand this and modify your code over here so that it automatically runs the tasks. So it doesn't execute get command, but execute command happens for player B. Okay. So this is the simple thing that you need to do. One thing you need to know is that if you provide a wrong command, the program would end by halting your gprolog. This is also a provided command so that you don't overrun your program and cause errors in the functions. So these are some of the safety inputs that have been provided in your code. To know further about it, go through this code, and a lot of documentation is available on this in Google. Best wishes reading that. So with executing these commands for player A and player B, you should be able to achieve your chess program that automatically runs the outputs for player A and player B. Best wishes writing your chess program. This is your first AI program using chess, and hopefully this will be an inspiration for you to do a lot more. Thank you.